All right, this next problem, I will just start out by saying it's a fairly difficult problem. It's one of the things I love about physics is that physics problems tend to not be one-step problems. You really have to go through and there's all these different nuances to it. There's multiple equations you have to use a lot of times. So what I'm looking at here, we have a 3,000 kilogram projectile which holds a 1 cubic meter gyroscopically controlled cylinder that contains 9 kilograms of argon gas. Ooh, that's a little crazy, right? Why would we have that? But hey, this is physics land, and in physics land, we can do whatever we want. The cylinder maintains an upright position throughout the flight, and the gas is trapped in a cylinder by a 320 kilogram circular piston with a diameter of 8 centimeters. Whew, complicated. The projectile is launched with an initial velocity of 150 meters per second at a 40-degree angle above the horizon. As the projectile reaches its maximum height, it collides with a larger object and falls undamaged. That's really cool how that would happen exactly. Straight down towards the Earth. How long would the projectile be in the air before it reached the height above the ground on its descent, where it would have enough kinetic energy to heat 2.67 kilograms of liquid water with an initial temperature of 1 degree Celsius to the same temperature as the inside of the cylinder of argon gas? So the truth is that there's no one part of that that's a particularly difficult problem to solve. The problem is, how do we start? So right now what I'm looking at is that I know I'm going to have to do some projectile motion and some kinematics in there. But the first thing I really need is I need time eventually, but I have to know about kinetic energy of the water. And in order to know the kinetic energy of the water, I have to know the temperature inside the cylinder of argon gas. So first, argon gas, that's what I have to figure out, okay? As soon as I see the word gas, I'm thinking, I bet you it's PV equals nRT. Well, let's see what we got here. Can I use PV equals nRT in this case? Okay, do I have the components? I have a volume. It's this metered squared thingy here, right? 1 meter squared gives me a volume. What about a pressure? I have a 320 kilogram circular piston with a diameter of 8 centimeters. And so that's what's holding it down there. So one of the ways to figure out pressure is that I remember that it's force divided by area. And so I think, they have this gyroscopically controlled, so it's always upright. So it looks like the piston is being held by gravity. So this turns out to be sort of semi-simple, I guess, really. And then, what about moles? Can I get moles? I have 9 kilograms of gas, so I can easily get moles from that. R is a constant, and then temperature is what I want. So yeah, let's do that. So I'm going to start off with force. So I'm going to take the force of the piston. So it's 320 kilograms, and I'm going to multiply that by gravity, and that gives me my force, 9.8. And then I'm going to divide that by the area of the piston. The piston is 8 centimeters. I need the radius of that, so that's 4 centimeters, but it has to be in meters, so we have to divide that by 100. So our equation is pi times the radius, which is in meters, which is 0.04 centimeters squared. Okay, there's our P. Volume is 1 cubic meter, which is equal to N, which is what we're trying to solve. No, I take that back. We're not trying to solve N. We have to get in. So to get moles, the periodic table gives us the molar mass of argon. So I can take my mass divided by the molar mass, gives me moles. That's the equation for moles. But I have to have it in grams because the periodic table gives me the number in grams. So I don't multiply that 9 kilograms by 1,000. Divide that by the mass of argon, which I believe is 39.95. 8.31 is my universal gas constant, and that's the way we can solve for T. So let's see what we get here. 320 times 9.8 divided by pi divided by 0.04 squared Ooh, that's a big pressure, 623,000. And then we'll divide out the moles, which would be 9,000 divided by 39.95. And then we'll divide that by the universal gas constant, and we get a temperature of 333.3, and that's in Kelvin, remember. So remember, gas laws are always in Kelvin. Okay, now that I have the temperature of the gas, I can figure out the energy of the water, okay? Because I'm going to use Q equals my mass times C times the change in temperature, okay? Water has a C, which is my specific heat, of 4186. And then the change in temperature, it says that it went from 1 degree to whatever temperature I have here. So this is Celsius, this is Kelvin. I can't use that. I have to, they're on the same scale, but I either have to turn this into Kelvin or this into Celsius. So I think I will actually just turn this into Kelvin. So let's set this up. They've given me a mass of water of 2.67 kilograms. And we will say that our C is 4186. And then we have 333.3 minus, remember that in order to change it into Kelvin, Celsius is to add 273, so minus 274. Okay, and that should give me my Q for water, which is pretty close, something I need there to go to my next step. 4186 times 333.3 minus 274 equals, ooh, that's a big number, 662,773 joules, approximately. Okay, now, the question is, how long would it reach a height before we're going to have enough kinetic energy to heat 2.67 joules? Well, that's what I need right there. I need that much energy. And so, at this point, I'm looking for height. So one of the things I can think about with kinetic energy is that kinetic energy gives me velocity. So if I'm looking for how long would it be in the air, that really says to me that I want time. So I'm thinking kinematics, and velocity is part of kinematics. So let's turn this into the kinetic energy equation. You know, EK is equal to 1/2 times the mass times the velocity squared, okay? And so that gives me an EK. We'll start with that, 662, and that's 773 is equal to 1/2. Now, what do I need for mass? How long would the projectile be in there? So I need the mass of the projectile, okay? They gave me the energy from water, but we need to say, okay, we're going to use this for the projectile. The projectile weighs 3,000 kilograms, so 3,000 velocity squared, okay? And so this is cool. It's going to give me V. So I'm going to take my 662,773, multiply it by 2, divide it by 1/2, whatever you want to do. Then we'll divide that by 3,000, and then I'll take the square root of it. Gives me a velocity of 21 meters per second. Okay, so I have this projectile. It's going up something like this. And it hits some object and it bounces down somewhere around here. And so I need the total time in the air. Reach the height, right? And so I need the total time in the air that it takes to reach that velocity. So I need to do two kinematics problems. I need one to get to that point and then one to get to this point. So let's do this point first. It's easy enough. I have V equal to 21. It's falling from being hit, so you know your vertical velocity was 0, so our U is equal to 0. I don't know the distance, but I do know the acceleration is 9.8, or negative 9.8, whichever you would prefer. And then we can solve for time, which is a simple equation, right? Z is equal to U plus AT. And so I'm going to start with 21 is equal to 0 plus 9.8, and then the velocity is going down, so that's going to be negative. This will be a negative, right? Anything going down, and then times time. And so just 21 divided by 9.8. So 21 divided by 9.8 is equal to, nope, I guess it's not a billion, hit the wrong button there. Okay, about 2.14 seconds. And then, I'm running out of room in my paper here, so let's see whether I can do this. How about right here? Let's try a new set of V's. So now I want to go up. All right, so I have to get this time here. And so I'm going to say, this is a really simple equation because I need to have I'm given, what? 150 meters per second at a 40-degree angle. So I know that this is initial vertical velocity, my u, is equal to 150 times the sine of 40 degrees. When I hit the top of this, even though I know I stopped horizontally, but I also stopped vertically even before I hit that, because it says that I ran into this object while it was at its peak. So my u, or my final velocity in this case, is 0. We know again the acceleration is equal to 9.8, and I can solve for t. So same equation again. I'm going to say that 0, that's my v, is equal to, let's see, 40 sine times 150 is 96 point, what am I doing here? 0 is equal, oh no, I'm sorry. My v, oh no, I got this all messed up. 0 is equal to 96.4 plus 9.8t. And so again, I'll have negative 96.4 divided by negative 9.8, so 9.8. And that gives me 9.83 seconds to go up. And so I'll just add the totals together. 9.83 plus 2.14, 11.97 seconds, so about 12 seconds. Phew, all that to just find out that it was going to take 12 seconds for it to get up, hit a projectile, and drop down. But each step really wasn't all that difficult. You just had to go through and find out, what did I have to solve first, then go to the next step. What do I have to solve next? Eventually, you can solve these problems. This is the beauty of physics, is that there's always a way of solving all problems. Someday we'll know everything. Well, maybe not.